Okay, hello everybody. I hope you can hear me well. Could you please confirm?
I can hear you.
Very well, thanks. So today the plan is to start something new in 585, something different that you have seen so far. So we turn a gear toward more theory and mathematics, right? So far, we had some interesting lectures on more practical aspect of how we can build reliable and dependable machine learning systems. But today, our focus today and the next few weeks, our focus is very much different, right? So we want to understand some basic of mainly the foundation of deep learning. That's the goal. So I would like to go and discuss some very basic theory, some basic stuff that build the foundation of deep learning in the next several weeks, and we start really with basic stuff. So today we will mainly look at perceptrons and logistic regressions, mainly discussing about linear algebra and some mathematics behind learning for these simple classifiers, mainly looking at linear classifiers. And then once we finish discussion about perceptron and logistic regression, the plan is then to discuss two different worlds. One world is about building such classifiers by probabilistic models. So something like naive Bayes, because I would like you to understand what are two different interrelated worlds for any sort of classifiers or machine learning, right? One view is probabilistic view, where we discuss the way of learning some naive Bayes and creating some probabilistic models and reasoning about the decision by building this probabilistic model. And then we go to more neural network stuff, right? And we discuss some foundation of neural networks by building smoothly from these foundations, right? So more specifically today, the plan is to discuss about linear classifiers, where we have input, typically represented by X. This could be, for example, in this particular case, a text, right? And then we have a feature vector, which mathematically is a simple vector that each location has a feature value, right? And each of these location in this vector is associated to one of the features of the model, okay? So this transition is basically, we have some sort of a model, right, in abstract way, okay? And then based on this feature vector, we are going to make a decision, okay? For example, in binary classifier, the decision is very simple, is as two classes, right? And typically, like You can call it positive, negative class. It depends on the domain. For example, if you're building a classifier for classifying whether a text is a spam or not, so you can call it a spam or ham, right? Or could be other sort of domain. If your input is an image, um, then the same process. You get some sort of feature vector, and you want to turn that to a decision. Whether what is inside this image. In this case, basically, you might be interested into learning whether in your image is 2 or not, or what is the digit inside this image, right? So the number of classes, if you're interested to learn what is inside the image, you have basically 10 different classes from 0 all the way to 9, okay? So it really depends on your application and X, the input space. And then we may have different number of classes. But we start off here by assuming that we want to build a binary classifier, right? So within this high-level overview, we have 2 different processes going on. One is turning this input to the feature vector, basically getting what these numbers should look like, okay, which has its own process, right? And depend on the type of technique, the process would be different, right? For example, for building a naive base, typically we need a probabilistic model, and in naive base, typically the case is that you specify some list of features. For example, in this case, you specify like some very so basically you manually specify these features, and these are not learned features. You manually design these features. You manually come up with these features, right? So you want to have like whether you have a word like free in this text or not, whether your name appeared in this text. This text is basically, we are talking about the email text. Whether you have any misspelled word in this text, whether this email come from your friend, and other features that you thought well, and you came up with this list of features, right? On the other hand, in neural networks, these features are learned. So the whole architecture basically, and the key benefit of neural network is that these representations and these features are automatically learned from data. And that's the key difference between something like naive Bayes or a linear classifier or multi-class classifier or some other version of traditional machine learning models, and the new type of machine learning models like deep neural networks, right? So in one hand, you have manually designed features. On the other hand, these features are learned from data. That's basically the key difference. And then you want to turn these features, but some magic, into a decision. And the key focus of these lectures would be on the other side. So we assume that this part, we are given this feature vector. We know the value of these feature vectors. And then our task is to basically do this magic, turning this feature vector to a decision, whatever it is, depending on the input space. Do you have any question about this? Because this is important to see the difference and clarify assumptions that we will be talking from now on. So there are some loose connection between basically the neurons inside our brain and the way how perceptron works. So in neurons, basically what we have in our brain, we have so many, like 100 billion number of neurons typically in our brain, human brain. Depends on the type of animal, this number would be different. And this is the overall structure of a neuron in our brain. So we have some places that we get input signals, right? These are dendrite, where we get the input signal to the core part of the neuron, in this case, nucleus. And the task of nucleus is to make that decision. So these inputs are fed into this nucleus, and this nucleus decide what kind of signal it wants to fire to the output, right? What kind of signal it wants to send out through axon to basically other connected neurons to this. Okay, so these inputs you can think about. For example, these inputs, some of these inputs might come from the other connected neurons, or maybe from some of our sensory inputs, such as eyes, ears, like through voice, through a smell, through many other type of input, sensory input, or like most of them may come from the other connected neurons. And each of these neurons, each of these dendrites have different strengths of connection. So some of them are loosely connected, some of them are basically has a more strength in the connection. So we have different types of dendrite. And these different types basically affect the way how this nucleus decide about the output. And these connections typically are through synapses, right? So these synapses connect, you can think about these as connectors between different neurons in your brain that basically connect different neurons and create the network of neurons. Right? In our brain, basically, we have one version of neural network going on there. Any question about this? So you can connect it to mathematics here as well, right? So you can define these inputs as some sort of values and some weights, okay? So these inputs may come from some values to this, and each of these might have a weight, right? I mentioned that the strength could be different. So we can imagine that this connection, we could assign some different weights here. So like you could consider here, right, some of these again with different weights that is showing the strength, and here you could assume that this nucleus decide based on a weighted average of these inputs, right? And the weights typically is shown through dot product of F with W, or sum over weighted average of F. And this is the way how you represent it mathematically, right? So you have some weighted average for producing the output that this will go out to the other connected neurons in the brain. Okay, so this is the way how it works, and this is loosely connected with the way how neural network and more simpler version of this in linear classifier works. So we have some inputs represented as feature values. Again, if you look at this, we are talking about this part, right? We are talking about that we have the feature values as input, and we want to produce the decision, right? So we are not talking about how to produce the feature value itself. We will talk about that later on, but now we mostly talk about this part. So we have some feature values. Each feature has a weight, and we need to produce some activation based on a sum over weighted average of these feature values. And the activation is represented by this dot product between weights and feature values. So this activation, you see that is associated to a specific weight vector for a specific input. Okay, X again is input, W is the weight. And the weighted average, which is represented here, is determining or defining the activation value associated to the weight. So in this situation, what part of this is learning, what we are going to learn, because make sure you understand this, feature values are given, we cannot change them, we cannot learn them, are given to us. So the only thing that remains is to learn some weights that produce this activation and produce the decision of the model correctly. So that's these W's are the things we are going to learn. So, for example, based on this activation, we could consider if the activation value is positive, then this is the decision would be associated to the positive class, one of those class. So we are talking about binary classifier here. So we have positive class, negative class. Okay, very simple. So we, if the activation is positive, then we associate it to the positive class. If it is negative, this can be associated to the other class. So this is one way you can produce the the decision based on the exact value of the activation. Okay, so basically this is the way how your model produce the output. And you can represent it in a block diagram. Again, this is very much connected to here as a weighted sum, each with different weight, and this produce the decision either positive or negative class. And this is basically the way how your model decide based on the activation that is produced here. So it's very simple. Mathematically is very simple and straightforward. Do you have any question here? Make sure that you're clear about everything, because this is the foundation of neural networks. So I would like you to understand clearly these foundations when we get more to the advanced stuff. So let's have an example. In this case, we have a specific weight vector, right? And we want to basically, the learning procedure is to figure out the right weight vector that produce the right decision for the model. So the key is to learn actually this correct weight vector based on a learning procedure that we are going to discuss now. Okay, so these are your feature values, right? And all of these, both feature values and the weights, or you can think about it mathematically as a vector, right? Vector in a multidimensional space depending on the size of your feature space, okay? So if you have, for example, two features, like you can represent it on two-dimensional space like this. If you have more, this feature vector and this weight vector lives in more dimensional spaces that obviously we cannot represent it here on 2 dimension, but you can imagine it mathematically, right? So these are mathematical vector that we are talking about. And then, right, so in this case, this is, you have one specific example that here in this case, you get, okay, for this specific example, you have two words, which is basically written as free, right? You, in this email that you received or associated to this particular example, there is no mentioning of your name, two misspells, and not coming from one of your contacts, right? So obviously there is some misalignment between this feature value and your weight vector. So your weight vector basically determining, okay, what are the importance of each of these features for you, okay? In this case, you're taking for free, if you have a word free, meaning that this is most probably a spam, so you put a high value for this basically feature associated to this feature. If you see your name in the text, you want to decrease the probability of being a spam. So the positive class in this case is meaning that this is a spam email. If you have misspelling, this is more probable that coming from a spam, but you want to put less weight comparing if you have a free in your text. And if it comes from your friend, one of your contact in your email account, then you want to associate relatively high that this is not an spam. So this is the way how you can interpret about this weight vector, okay? So the dimension of this weight vector is the same dimension as your feature vector in this case, okay? So if you think about this, so you see that in this example, you have two number of frees, two misspelled, and if you do the dot product between these two, you see that what you get is 4, 2 plus the next one is 0, right? Plus 2 plus 0, okay? So this is positive, this is 10, okay? And that's why you see the alignment between these two. So in the vector space, these are aligned. So meaning that the decision for this particular example, so this particular example is actually a spam, or at least this model thinks that this is a spam, okay? This is the way how model thinks, because it has a specific weight, and obviously these are coming from your data from X1, and the current way with this weight, the model thinks that this is a spam. It might be the case that this is not actually a spam, but the model currently thinks that it is a spam. And you get another example, right? This is another feature vector associated to X2. No free mentioning, you see your name, you see one misspell coming from your friend. So this is probably not a spam, right? And you see that if you do the dot product, you get 0 plus minus 1, right? Plus 1 plus minus 3, okay? So this is minus 3. And this is associated with negative class, which is model thinking that this is not a spam, and that's why you see that like these are not aligned. There's no alignment between the weight vector and this feature vector. And typically, like if you want to visualize it, you could consider a hyperplane like orthogonal to this feature. So you could consider hyperplane here, and a vector. If a vector lives here, right? These are belonging to the positive case. If a vector lives here, right? This belongs to the negative class. Do you have any question about this?
Yeah, I have a question.
Yeah, go ahead.
And so this type of vector type of evaluating the input versus, you know, your set conditions, this only works for a binary decision. So, but so anything where you're deciding between two things, and I guess my question is, does it work if you're deciding between any two things, or only if two things that are mutually exclusive? Like if the two things add up to 100%, or is it just when you have two choices, period?
That's a very good question. So when you have two choices, right? We will go shortly to multi-class classification, where you might have more than two choices, right? You might have 3 classes, you might have 4 classes. But we started from binary classifier, and where you have two basically disjoint choices, like in this case, like a spam or ham, could be like male, female, right? Could be cancerous, not cancerous, kind of thing. For example, for a classifier determining whether like this tissue is a cancerous tissue or not, right? This is a binary classification, right? And you have so many of these binary classification cases that is out there, but we start from this because like making sense out of this and visualizing this is so intuitive, and we understand it well. Because when it gets to multi-class cases, it becomes less intuitive to visualize.
Right. I guess I probably misphrased my question, but so for this example, like I understand why this works well for a binary case, and how it's super easy to understand. But I guess my question is, why is it possible for you to use the same technique but to set ranges, or does a vector style like this only work for binary, or is it just like best for binary and we're using it in this example because it's intuitive? Or could you say like, if the dot product was less than -3, send it to 1, make one decision, but if it's between -3 and 1, make another decision, and if it's greater than 1, make another? Like I guess, is it necessarily binary with the weight vector, or are we just using a binary case because it's the most intuitive to understand?
Actually, the latter, right? Because it is most intuitive to understand. But I think your question will be clarified when we get to multi-class, right? So when you see the differences and how you could make sense of going from multi-class to 2 classes to like 3 classes, right? This transition, I would say, help you to understand why this particular case of binary classifier makes sense and why it is so intuitive. Because then become a lot less intuitive in multi-class. But yeah, this is a very good question. Thanks for asking it. Because then it makes things a lot clearer when we do this transition.
Right. I mean, also in theory, you could set up a pretty complicated model that only uses binary decisions, but it's just interconnected binary. It's like a bunch of binary decisions based on different parts of the input. I guess that's just like me thinking abstractly, but
right. Maybe you are thinking about maybe you could split a multi-class to several binary classifier. Then that doesn't work. Maybe you could, but then that would become ad hoc, or because the mathematics behind multi classes would be well connected, but slightly different. The way how we have mathematics behind multiple classes, right? It's not straightforward to split a multi-class to several binary classification.
Right. They're different, right?
Yes.
Yeah. This is so different. Yeah. Okay. I got you.
Okay. So let's discuss about the decision rules, right? Because these decision rules determine the decision made by the classifier. And typically here we have some examples of 2 different kinds for binary classifier. Some of them belong to one class, the other one belong to the other class. And really, when we say learning, it's so simple as separating these 2 classes. So when we say learning, we learn something. We typically, it boils down to putting this separator between classes. This separator is really the decision boundary that you need to learn from data. So you have data, you need to learn this thing, and this is the result of your learning, what we call basically the decision boundary of your model or your classifier. So it's simple as that, and you really learn this decision boundary from your data. And in this case, like your data is so much easy and separable cleanly by even a linear decision boundary. So you see that this is a linear decision boundary, it's not non-linear. And when it comes to linear models versus non-linear models, like this is the way how it looks like. Okay, so here you're talking about the binary decision rule. We have some examples. These are the points here, right? Any weight vector is a hyperplane that we discussed, right? Which one side correspond to one class, the other side correspond to negative class. Okay, so and here, like, imagine that you have two features, right? To make it easy, then you want to have a separator. This is the decision boundary. This is a linear separator between your classes, right? Which this part you can correspond it to the negative class, this thing. The other side you want to basically associate it to the positive class. Okay, so and the learning really looks like, okay, in this two-dimensional space, how I want to move this decision boundary, like whether I want to move my decision boundary here, or maybe here, or maybe like here, like so. And at the end, it is like, since it is linear, it's a hyperplane, right? That lives in these high dimensional spaces, in this case, two-dimensional spaces, and you have some flexibility to move it around. And this is, you can correspond it to the complexity of your decision boundary. So like this is linear, is so simple, your decision boundary. And when we get to more non-linear models, like deep neural networks, these become obviously non-linear. The decision boundary is non-linear. You have different sort of complexity for your models. So you can make a sense out of this if you want to. Any question about this? So the learning, it really boils down to updating the weights. Okay, so here again, here in this case, updating weights is like learning where should we put this hyperplane, this separator, linear separator, and how we should do that. What is the mechanism behind the learning, and what it means learning from data. Okay, so far we have not discussed about learning yet. We just try to make a sense out of the decision by assuming that we already have some learned weight vector. But now we want to discuss, okay, how the learning itself looks like and what it means by learning, what we mean by learning from data. And this really boils down, okay, how to update this weight vector. This is simply the core concept behind learning. This is a very simple procedure for learning a binary perceptron. Again, this is a specific model that is started, Perceptron, a very simple model. And this is the learning procedure for learning this, right? The core concept, when we discuss about some other type of model, even neural network, you see that like the whole concept is very much similar. The underlying mathematics is more or less the same. It's some like small differences, but the thing that you learn here is core, would stay the same like for the rest of the stuff. So we start by like some initialization. Typically, the weights are initialized by 0. Right, so for each, we look at each example, the training instance. We classify with the current weight. So this is the current weight that we have. Like we started by 0. And then like for each example that we have, we look whether this example, given this weight, has been classified correctly or not. How we can make sure this has been classified correctly or not? This is very easy because we talk about training instance. When we say training instance, we have the supervision. We have the correct label for each instance. So we know that this is actually not a spam. This is a spam. These are basically training examples that you know its label, the ground truth. You know the ground truth. And we use this ground truth as your supervision. And that's why we call this supervised learning, because we have the supervision for learning. We know the correct label, we know the correct signal, and we use this signal to update your weight vector or to update your decision boundary or to do your learning. All of these are the same. Okay? Make sure you understand these terminologies because these are important. And then you look at each example one by one. If the decision that was made by your classifier, Y represents the decision made by your classifier. Remember, what was that? Y was how you determine the decision? Simple, right? So you calculate the activation. How you calculated the activation for this particular example given weight? So you have the weight, the same weight, you have example, this is the example, you calculated the dot product of W, right? F, sorry, you have to wait a few minutes. So you calculated dot product between W and your feature values, right? And this activation, once you get it, so you look at, so how, based on this activation, you determine the Y, right? So if the activation is like larger than 0, you want to say that Y is -1, is activation is negative, you want to say that this Y is +1, something like that. Okay. So this is the label that is given by your model. This is different from Y star. What is Y star? Your ground truth. Okay. So there could be technically difference between your ground truth that you use as your signal for supervising your training, and this is the decision that has been made or created by your model. So there is differences. But if the decision that has been made by your model is correct, so obviously you don't want to make any update to your weights, okay? Because your model is good enough. Good enough for what? For this particular example. So you need to repeat that for all examples, right? Not enough for one example. You need to repeat the whole procedure for all examples. If the example, right, for example, in this case, like was this, right? If the example is wrong, then you need to adjust adjust your model, right? Here, in this case, your weight vector was okay, but in this case, the ground truth says that there is a divergence. The ground truth says that this is negative, but your model says that this is positive because it belongs to this part of the decision boundary, the other side. So this is wrong. Basically, in this case, Y is not equal to Y star. Okay, and because of that, you want to adjust the weight vector. So you need to move this toward this, maybe like making this like this, right? You want to do some adjustment of this decision boundary in order to make it correct for this particular example, right? And you go through all example to do this adjustment, okay? Is there any question here? Next is how mathematically we will do this adjustment. Give us 1 minute. Think about this, what I have said. We'll continue next. How we will do this adjustment mathematically. 1 minute. Okay, is there any question? So now let's review how this learning looks like. What is the mechanism for doing this update to the weight vector in order to say that we have learned from these examples. Okay, so it gets a little bit more mathematic stuff, right? So again, we start by 0, and then we classify with the current weights, right? Meaning that we calculate this dot product and we get uh, the result of the model, and in the feature in the space of vectors, it means that like if your weights and feature vector are aligned, this is positive, right? You know that from linear algebra, if two vectors are aligned, the result, the dot product between these two are positive. If are not aligned, for example, in this case, the dot product is negative. And again, this is given. You can not learn it. What you learn is W, or what you update is W. So in this case, no change, you are fine. If wrong, you need to adjust the weight vector by adding or subtracting from this feature vector. Sorry, from the weight vector by some value from your feature vector, right? So for example, you can do this. So you can update your weight vector, right, by adding this term, the dot product between y star. This is the correct label of this particular example, right? In this case, it's -1, right? And dot product with your feature weights, right? So basically, if the weight, if this particular case, for this particular example, if the decision made by your model is incorrect, you need to do this adjustment to your weight vector, right? And this is very simple, right? So meaning that if you want to make a sense out of it, meaning that if your your weight vector for this particular example is not aligned with your feature vector, you want to like move it in these high dimensional spaces, in the space of dimensionality. Again, this depends on the size, the dimensionality of your weight vector and feature vector, right? You want to make it aligned with this particular example, right? So you basically move this along to make it aligned for this particular for this particular case, right? So it's basically meaning that you move around this weight vector in this space. So in this case, what you have here is basically you want to move this weight vector by this adjustment, right? So this adjustment telling you that this weight for this particular example should not well align with the F, because the decision, if y star is negative, it belongs to the negative class. But this current vector that you have for this particular example producing the positive class. So it's basically is well aligned to this F. So you need to move it away for this particular example. And the way how you move it away is to add this. Since y star in this case is negative, meaning that you subtract these feature values from the current values of your weight, and this will move basically this weight vector away from F in this case. Okay. Does it make sense? So for example, in order to make a sense out of it, so think that way. Let's make a sense out of it here. So you updated W with W prime, and then you now, after this update, you want to get the dot product with F, right? You want to see what you did with your model after this update, okay? This is the way how you can think about this and see what we get really. So what we get is that, let's replace W with what you had before, right? So we replace W prime with W, Y star dot F, okay? This is what we did, simple as that. And then we get WF. What was this? Can one say what was this? What this represent? Any volunteer? I'm waiting for you guys. I hope you are following. No volunteer? It's very easy. Don't worry. It's not a good sign that we don't have any volunteer. So I call you guys. Stephen, do you want to say something about this? No? Are you listening? Apparently, Stephen is not listening. So how about Cody? Do you have something to say here?
You're asking about W dotted with F?
Yes.
That, I believe, represents how far, like, when you dot two vectors, that represents whether or not gives you, like, I guess, how far in the same direction they're going. So W dot F kind of gives you an indication of, like, how far off one vector is from another, I believe.
Yeah, but what was this before? This was like before this update, because we are talking about W. W was before this update, right? What was this represent?
before the update, I don't believe I'm following. Before the like this is a training step, right?
Yes. So before this one step update, right? Before this one step update, like we had W, right? And we updated W by something. This is the thing that we updated, right? Like this is, come on, this is very simple. W dot product by F was the decision that has been made by the model before this update. Simple as that,
The
right? So
past prediction.
yeah, it was past prediction, right? And this past prediction was incorrect, right? So we wanted to update that. Hopefully, with this correction, we make it somehow more correct, right? We make some correction into the decision that has been made by the model, right? So this is like the decision by your past model. So basically, if this was W, like let me clear this. So this was your W, this was your F, and these were aligned. For this particular example, your Y star, your true label, saying that this is negative, right? But like this dot product was somehow positive, okay? This W dot F was positive. So you want to make the correction by like doing something, and this is the correction you make. So you are doing Y star dot F dot F, right? This is the thing this is the correction that you make to your model. So this part, we know that this is positive, okay? Y star is negative, -1. So meaning that this correction, we basically, whatever value this has, we are subtracting this from the previous activation, right? So we had some activation, we subtracted something from that. So this activation was positive, meaning that the model would give you the positive class as a result. So obviously this is not good enough. You want to subtract something from it. And the way how you subtract it, you added this term, Y star dot F. So obviously this should make sense. And here we made a sense out of it because like we expected that the training would subtract something from the current activation because the current activation doesn't make sense for this particular example. And this is the way how the subtraction works. Does it make sense?
I believe so.
Okay. So basically, we move this weight vector away from your feature vector with the hope that your model next time after this correction make a correct activation and decision for this particular example. And this was one example. You need to go through all examples. Maybe this correction make some other decision for the other examples incorrect, and you need to go through all of them to make sure that the model would make a right decision for all of them, at least for your training, because this is the only thing that you have. Okay, so this is F is the hyperplane, and like you play with this weight until you get it right. So in this case, you have some examples. These are like examples that, again, training example. In this case, you see that obviously there is a separation, linear separation between these two sets of examples. So you should be able with a perceptron to separate that. Then you might start with this weight, this is your W. This is your hyperplane that you start with, okay? And then you want to adjust this weight until you get it right. Obviously, this is not the right, the right weight because you got some example incorrectly, right? So you need to adjust it along the way, right? And this is the way how it works, right? So previously the weight was living somewhere. You had this example in order to, maybe it was here, right? Considering this example, you need to move it to make the decision correctly for this example. So you need to move it here, right? So this is the update that you made. And then with that update, you needed to consider this. You need to make this adjustment to make this correct, right? And so on. Then you have this. You need to adjust it again. So this wiggle around until you get it right. So then you had this example. You need to adjust it, and then until you get everything correct, right? So this weight vector should move around in this case, like you have two-dimensional space. Like we could not visualize it for like more than 2 dimensions. But this is basically the mechanism how it works and how it looks like. This was a learning procedure. When we say learning is not like something crazy, it's simple as that, right? You move around your weight vector until you get this decision boundary correct to separate these two classes for you. And this is basically the whole mechanism behind binary classifier, how to learn a simple perceptron to separate out two different classes. The next would be moving to multi-class decision and how to learn a classifier when we have more than 2 classes. The key intuition is the same. We do the same sort of updates to the weight vectors, but let's go into the detail of this in the next lecture because this transition is also important and we want to go into the detail to make some intuition. This binary classifier is very easy, is intuitive, but this multi-class classifier is less intuitive. So let's stop here. I would wait for a few minutes and then if you have any question, please do ask. But we are done with this lecture today. Thanks.
Thanks. Oh, there was a question in the chat. I think there might have been others.
Benjamin is asking, if your model predicts incorrectly, will it keep using the same training example until it gets the example right, or it just move on after making a correction? Yeah, your training examples are fixed. I'm not sure I understand your question, Benjamin. Could you speak? Benjamin, can you ask your question verbally? No, I'm not sure I can understand your question. But basically, your training examples are fixed, or you assume that it is fixed. and you make this correction until you were able to find this separator. You might have the case that like there is no convergence guarantee here. So maybe you cannot, like if you do this forever, if you have cases like you have this thing here, right? You might have these examples here. So obviously with binary classifier, you cannot separate out this because there is no hyperplane that could separate this linearly, right? Um, you have to leave, you have to stop somewhere unless like you want to go forever. And that's why there is no convergence guarantee here. But if your data is linearly separable, it will find it. This procedure will converge to a hyperplane in order to separate them linearly.
Okay, yeah, that makes sense.
Thanks. That's a good question. Any other question? If not, then done. Thanks. See you soon.